Okay. Okay, so hello everyone, and welcome to our lecture on Battlecode tips and tricks. So in this lecture, we're just going to be talking about our experience in Battlecode and some, I guess, ideas that you can think of as you compete this year. So to start off, let's just talk a little bit about who we are. So, so Johnny and Daniel first did Battlecode in 2022, and then Max joined in 2023, and then I did Battlecode my first time last year. And together we won the high school division last year and we placed second overall. And so far this year, C Log Will Log is currently on the first page this year so far. So that's definitely pretty good. Um, so, so this presentation is mainly geared towards beginner and intermediate teams. And we're just going to be talking about some applicable techniques that everyone can think about and try to implement in their own bots. We'll also be talking a little bit about some niche advanced techniques like from previous years. And the lecture mainly is going to be rather sporadic. Like there's no like general topic, but we're just going to give you a bunch of different ideas to think about for this year's game and see which ones you're interested in and which ones you want to like implement, I guess. So I guess the first thing we want to talk about is something known as polymorphism, which is basically a way to organize your code and make it more readable. The idea is instead of just writing all your code and shoving everything into like robot player, it's often a good idea to create different classes for each section of code. And this, I guess, creates like a much more organized code dynamic and allows you to like debug and like modify your code. And like, for example, like all robot are robot objects, like a splasher is both a splasher and a robot in the context of this year's game. A mopper is both a mopper and a robot. So here we have like a diagram just to show the control flow of what your code might look like. Like we have the main robot.java general file where we do all our things like set globals, read comms and other functions. And inside robot.java, we have other specialized files for like different robots like splashers, moppers, and soldiers. And in each one of them, they have their own like, things they can do, like actions and whatever, like micro strategies you can implement. And then we go back to robot.java, where we complete the turn and do whatever other useful things we need to do. And then there are also other static classes or other files like comms.java, map.java, that are also useful. These are static files because we don't like instantiate any instances of them. And those are also part of the work, the control flow. Okay. Hold
Uh,
on. All
yeah.
right. All right.
So I guess like just an extension on like the previous stuff, like all of this, like if you compete in Battle Code multiple years in a row, you'll have this sort of framework set up. So whenever we start, we just copy like the entire like polymorphism hierarchy and all the files over.
Wait, wait,
So
hey, wait, Johnny, can you stop talking for a second? Wait. Huh? Oh yeah, pause for a second. Pause for a second. My bad. My bad. Wait, my bad. Wait. We're trying to get the volume to work. We're trying to get.
Wait, I don't know how to do it on a Windows. Is it like something? How do you? It should be this.
I don't know. Hopefully.
Daniel, can you hear me?
No.
Okay.
Wait, is this fun or wait, is it?
Wait,
Uh,
I checked the YouTube stream and it seems to be working. So,
Really?
yeah, I don't know. I
Maybe
heard you
the
talking,
uh,
maybe it doesn't work in the room.
maybe.
we're trying to like figure out how like to get the speaker stuff to work.
Hmm.
Um,
I don't know. It seems to work on YouTube. So,
Let's stop on Zoom, dude. Oh, I see, I see. Okay. Oh, I see.
You try again. Wait, can you try?
You hear me?
Oh yeah, that's good. That's good. That's good. All right.
Okay. So I guess what I was saying before was like just a quick extension on the whole control stuff. Like I found like in our experience competing like multiple years in a row, like once you have this sort of structure set up, you can just copy it year from year, and it's really helpful to get started quickly without having to rewrite all like the boilerplate code. So I guess the next idea, and I think what's been most helpful for us is like to learn battle code, it's really about like stealing ideas from smart people and seeing how you can use them effectively. And maybe you'll find some things by yourself along the way. Next slide. So obviously we have XSquare, and XSquare has been incredibly successful, like multiple years in the past. And basically now everybody's code is in probably some way inspired by him. And most notably for us, there's two things that he did that really helped us out in our code. The first thing is his microstructure, which we'll talk about a little bit more in depth. And then also his unrolled BFS. And a general trend you'll see with a lot of these things is when you're designing heuristics and writing the bot, simple is better most of the time. So specifically for XSquare's micro, the version we use from him works in the following way. So essentially, this is for moving or picking some square to attack. And essentially, what's going to happen is you want to compute some sort of weight or properties for each square. So specifically in the movement case, in the bottom, you see your location in the center, and then you want to decide which direction to move when you're in combat. So that's like a sort of micro strategy where you're considered just with like, how can I maximize my own result when I'm battling in what I can see right now. So what happens with XSquare's framework is he reads in all of the enemies in the area and friends, and he uses them to update information for each one of the squares in the surrounding positions of your own location. So for each of these squares, you compute the closest, how far the closest enemy is, how far the closest friends is, how many enemies can possibly attack that square. And afterwards, it's really easy to design a heuristic to choose which square is better. So essentially, then you set up a comparator function which compares like if a single square is better than the other. Um, if you want, you can click into like the GitHub code real quick, and we can see like a more concrete example of this. So going down at the top, what this is the main body of it. So yeah, scroll up a bit to the process term. So yeah, here. So what happens is all of these informations are read in, and then you calculate, if you see down there, there's a loop that goes through all of the enemies. And then for each of the squares, which we represent using a class called microinfo, we update the enemy with it. So basically for each of these squares, then it computes like the closest enemy. And then scroll down to the bottom. So in the class microinfo, all of this information is computed. And at the end, the function you saw we're in is this is better function. And with all of the information we've computed, then we can design a very straightforward heuristic. So for example, at the top, one of the most intuitive things to do is obviously if you cannot move to a square, we shouldn't try to move to the square. So when comparing this to another microinfo, which again represents a position, if you can't move to that our position, then obviously the current one is worse than the one that we can move to. And a lot of the different heuristics like this, like you want to minimize the amount of damage being done to you. And really messing around with this structure can help you design a very clean heuristic. Back to the slideshow. And go on. So overall for this structure, like it's very clean and modularized. So it's like one thing we noticed when we started is that when we were writing these heuristics, it was a lot of if statements like, oh, if our health is greater than this, we should do this. If our action cooldown is this, then we should do this. And it gets really messy once you have a bunch of if and switch statements. And adopting XSquare's style of kind of simplifying things and keeping things clean, it makes the heuristics a lot easier to read and tweak. And a con might be it costs like a bit of bytecode, but a bunch of the operations you're going to be doing anyway, so it's fine.
Yeah, so another piece of code that was inspired by XSquare was Unrolled BFS. Nowadays, a lot of the top competitors do use it. Not so much this year, but for the past couple of years, they've been using Unrolled BFS. It's useful for navigating tricky maps, but since this year only 20% of the map are walls, it's a little less necessary. But so how it works is that for loops are expensive. So when trying to create a regular BFS, it tends to run out of bytecode. A regular BFS takes like 10,000 bytecode usually. But unrolling it can cause it to half in the cost of bytecode. So you can go from like 10,000 to like 3 or 4,000. And this unrolling BFS does create a lot of code. So for example, our BFS code totaled to around like 10,000 lines of code. So how it works is we created a Python program to write the Java code. And I can show you how it works on the next slide. So basically how we start off is we compute each of the locations, and each of the map locations can be computed so that we can sense the whether there's a wall there or not. So we first create each variable, a bunch of variables for each possible location, and then we sense each location and sense whether there's a wall, whether there is water, and whether you can move onto that square. And then after that, you essentially on the right side, you have the BFS portion, where if you can move onto that square, then you can calculate ret for that value. So each of the rets holds like essentially how far or how much cost it takes to move to that square. So yeah. So if you move to the next square, next slide, you can, what we do is we consider each of the squares, and then we consider the how fast you approach your target by doing the initial distance minus the square root of each of the map locations and divided by the how much it costs to reach that location. So ret is essentially a way to count how many turns it costs to get to a certain direction, get to a certain location, and then we have we want to minimize the cost it takes to get to that get to a certain location, or rather we want to maximize the speed we approach any location. So we have Cmax, and then we have the answer, which keeps track of the best direction to move towards. So yeah. Next slide.
Yeah. So next, we have Chen YX, who is from Gone Fishin', Gone Sharkin', who was the winner of last year, and he has a lot of interesting ideas too. There's a lot of other competitors. We in this slideshow we only covered X squared and Chen YX because based on time. But for Chen YX's ideas, there was one idea specific to Battlecode 2024 that we stole from him and helped us a lot. And then also, he has a very interesting take on randomness, which is good. Next. So one specific thing from Battlecode 2024 is an idea that ChenYX actually shared with us or shared with the whole Battlecode call during probably after a sprint tournament where everybody's just in the call and sharing ideas. So the actual specifics aren't that important, but essentially last year there were spawn pads where you had to spawn a robot, and if you wanted to win a game, it would be really helpful to camp around your opponent's spawn pad. So whenever something spawned, you could kill them instantly. And so in this way, you wanted to be able to spawn troops at your spawn pad when your opponents got close and also defend that territory. And in that way, a lot of teams kept a robot sitting at their spawn pad the whole time so they could communicate when to defend. But ChenYX had an idea to exploit an idea, basically having one robot to not spawn at all and checking if the spawn pad positions were open. And if they were not open, it would either be two cases. It would be either your robot is standing on it or your opponent's robot is standing on it. So you can communicate if your own robot's standing on it. So if you get any anomaly, you know that your base is being invaded and you can spawn and defend. But I think like the important part of here is basically there's a lot of great ideas like in the Battlecode server, and we spend a lot of our time perusing, reading the strategies page, seeing what other people have to do. And obviously in the voice channel, there's going to be a lot of great ideas too. So we thought that was really helpful.
Yeah, so another one of ChenYX's ideas was to treat for pathfinding. A lot of the time, when you're trying to pathfind around your own robots, when you're trying to do bug nav around your own robots, it's very hard because you essentially have walls that are moving. So one way that I think was suggested by ChenYX was to treat robots as walls 80% of the time and 20% of the time as passable. So you treat like a robot as if you can move onto that square. So this allowed robots to both not get stuck against other robots. If you treat them always as passable, you can have instances where you get stuck, where you both think you can move forward when in reality you cannot. And if you always treat them as walls, uh, you have essentially moving walls, which makes the bug nav very complicated. So yeah, using randomness can be extremely helpful. For example, with exploring as well, we use randomness. Like we'll have like if the ID mod, for example, 3 is less than 2 this year, what we did was if ID mod 3 is less than 2, we would like explore. But we changed our code anyways. So yeah, it didn't end up working out. But yeah, like randomness is generally pretty helpful. So yeah. Next slide.
Okay. So now we're gonna just talk about some more general things on how to improve. So first thing is it's important to like keep your code clean, as oftentimes your battle code files can get quite long, and it's often your code is often going to be rewritten or heavily refactored. Like maybe you want to modify your code or incorporate some new thing that you saw. So it's important to keep your code clean. Another thing is you want to have many small functions as opposed to like a few big functions. That makes testing like a lot easier, and it just keeps code organization like a lot better. And it's also good to have more versions of the code, like especially like for testing purposes, like if you want to test a previous version of your own bot. And sketchy code is bad code in the sense that like you have to make sure that you like understand really precisely what your code is doing. Uh, like, and as we've said like multiple times, like simple is better. So like oftentimes people will think, oh, maybe the most complex or the most convoluted strategies are the best. So like maybe I have to do some big brain idea or whatever. But oftentimes like if keeping it simple will often actually help improve your bot. And then obviously there's GitHub, or you can use diff checker. Those are and diff checker, there's the link there. Those are ways to like, I guess, help improve your code and stuff like that, to see if there's any differences or I don't know, just to help you while you code your bot.
Yeah,
Uh,
so div checker basically like the tools there, it allows you to like merge your code. So it's a website that shows you like the difference between like two files. And basically GitHub does the same thing, but we're kind of bad. So GitHub is yeah.
yeah. And then a few more things are like, first of all, like you should scrimmage a lot and watch and analyze your games. And you want to watch your games slowly. So first of all, obviously you want to see how your own bot is doing, as well as you want to analyze like what the opponent is doing and see if they're doing anything like interesting that you can like, I guess, take into account. And as we already said, it's good to keep multiple versions of previous bots. Oftentimes, like in Battlecode, when you like make a change to your bot and you want to test to see if your new version is better, like oftentimes like you won't see any like immediate like big difference between your new bot versus your old bot. Like it might still be like a 50-50 kind of thing, but obviously it's still like good to keep your older versions just for future reference in case you ever need to like look back on them or test it or anything like that. Also, it's good to add improvements gradually. Like you don't want to like like put in a bunch of things at once. Otherwise, it's hard to see like what exactly is like making the bot better or worse. And also like don't spend too much time tweaking the numbers initially. Like of course it could be useful to like kind of fine tune some of the parameters in your like heuristics and whatever, but it's more important to first come up with the ideas, and then after the ideas are established, then you can try to fine tune the numbers and try to make it better. Um, I guess let's also just quickly talk about a little bit about pathfinding. We had an earlier lecture on pathfinding, so I'll just quickly just go over this. So there's like greedy pathfinding, which is just from any given location, if you want to get to the target location, you just move in the direction that is most optimal in the moment. Of course, that isn't always like going to work with like obstacles and stuff like that. And then there's bug nav, which we also covered in a previous lecture, which is, if you ever hit a wall, you just kind of like follow the wall. And then like, basically it's like, and then every time you get like not stuck, you can like keep moving. And then it's like, but oftentimes like, and then there's BFS, which is like, breadth first search, which is, I think we already talked about BFS a little about unrolled BFS. And obviously like the reason we can't use BFS to search the whole map is because like obviously that requires too much bytecode, but I guess some things you can consider are like you can think about performing the search in a local area, like along like some like vision radius and store that information. You can also think about distributed BFS, which is like if multiple robots all like do some kind of BFS and like communicate it to some like shared array. And then there's unrolled BFS, which we already like talked about.
Yeah, so a couple of micro tips is to, well, first of all, use like XSquare style micro. It's like very useful. A lot of times you just changing the order of the priority in the is better function is often the way to improve your micro, and oftentimes small changes make big difference. So yeah, and then there's also Lanchester's laws, which I will derive on the next slide. But basically, what it says is the strength of the army is proportional to the square of the number of soldiers. So, um, oftentimes it's better to clump your army together in modern warfare, I guess. Like a lot of times you have armies marching together, right, rather than splitting up your army a bunch, because when you split up your army does get weaker. And I will show derive Lanchester's law on the next slide, so I'll go over that later. um you can also use randomness. For example, last year, if the ID mod 3 was less than 2, uh, I made the duck into a healer duck. Otherwise, I would make it into a attacker duck. And then, yeah, so attack radii is very important. So yeah, next slide. Yeah, so here's a specific example of why like a lot of the top teams, the bots, move in and out of move in and out when attacking. It's because, for example, against towers, um, you can actually get up to double the attacks since towers cannot move. So how this works is the tower has a larger radius, so the tower attacks, and then the robot moves in range and attacks. Then the tower attacks you back, but then the robot moves, attacks, and then moves out of the range. So like so in reality, the robot gets to attack twice, whereas the tower only gets to attack once because um you can attack and then move at the same move. So rather than trying to um face the tower head on, you can attack. You can move in to the tower's range, attack the tower attacks you back, and then you attack and then move out, so the tower can't attack you anymore. So yeah, and this works against other bots as well, other like soldiers or like anything else as well. So yeah, and then next slide. Yeah, so how Lanchester's laws work is you basically assume every troop can attack every other troop at the same time, which is a pretty big assumption to make. But like, so in reality, Lanchester's laws doesn't entirely hold, but making some, the idea is very similar. So how it works is you have the let X be the size of one person's army, and y be the size of your opponent's army, right? So the change in the size of your army is proportional to the size of the opponent's army times like some constant a, right? Depending on how strong their soldiers are, whatever. And then the same thing can be said for your opponent's army. The change in your opponent's army is some constant b times the size of your army, right? So you have more soldiers, they'll decrease in army size quicker, right? So it's pretty intuitive. You can divide the first equation by the second equation, expand it out, and then you get b times x dx equals a times y dy. And why this is useful is when you integrate both sides, you have ax squared equals by squared plus c. So this equation always holds up to, and then the c is a constant, right? When you're integrating, you have a constant. So then when you subtract on both sides, what this equation basically says, it says that the size of your army squared, the strength of your army is proportional to the size of your army squared. So why it says that is, well, consider like if you have a super large army versus y, which is a smaller army, right? So let's say x has, I don't know, like 10 people, y has like 5 people. So then you have the difference, a times 100 minus b times 25 will be constant. So whenever when you lose someone, right, essentially what happens is when x goes down by 1, y will go down by a lot more than 1 because you have to have that x squared minus y squared is constant. So this basically says that like having larger armies is more beneficial because you can win more convincingly. Essentially, if you have like a 10 soldiers versus 5 soldiers, you'll end up having 8 soldiers left alive to completely wipe out the opponent army, instead of how you would intuitively think 10 minus 5 is 5. So yeah. Next slide. So yeah, macro strategies, it's good to explore at the beginning, obviously. There's a way to calculate the map symmetry by just going in 2 different directions and then communicating like what symmetry the map has. And this can help you find enemy ruins and enemy bases in the last year's case. And then you have coordinating units to target a specific place is pretty useful because the more, I guess, clumped your army is, the stronger it is relatively. And then economy, last year you just spent crumbs whenever, but it's often good to like have a good economy, have equal paint and money rather than like having like 30,000 like coins and like 0 paint. But yeah, next slide. So yeah, so we basically, I think we're running out of time, so I'll just give a few tips for this year. So in 2023, what happened was our one of our team members created an offline BFS to compute the optimal path for carriers to come from like mining to deposit to your base to deposit materials. And offline BFS, by that I mean like whenever you have extra bytecode, you can use it to calculate the BFS, and you essentially store what you've calculated so far because you can't calculate the BFS all in one turn. You just don't have enough bytecode for it. So whenever you have bytecode left, you can use that to calculate BFS. And then another tip is keep a good economy for both paint and chips. Mopper micro is pretty important, I think, this year. So it might be a good idea to unroll code for Mopper and Splasher attacks. Not saying whether we do that or not, but yeah. And then SRP, here's a pretty simple like idea for SRP. You can stack SRPs like in the image in the bottom right, and what you do is, a simple way to do it would be if the x coordinate mod 2 equals to mod 4 equals to 2 and the y coordinate mod 4 equals to 2, make that the center of an SRP. So and then you build around that. So it's like a pretty simple heuristic, and it works pretty well, I think. A lot of the top teams use it. I think Cal uses it, and we also use it. So yeah, it's a pretty good heuristic, but obviously the developers can screw up your code by just making everything like uh, a distance of 4, so you can't make any SRPs. But hopefully there's no edge cases like that. And soldiers are kind of OP against towers this year. Like 2 soldiers can take out a tower pretty convincingly. One soldier can almost take out a tower. So yeah, so like the soldiers costs like a tower costs 5 soldiers basically, 1,000 coins. But you can use 2 soldiers to kill a tower. So that's like kind of OP. Hopefully they either buff towers or nerf soldiers or something. We'll see what they do. And then yeah, try a lot of different things, because a lot of the times there will be balance changes. So like you never know when, like, if something you tried previously might become meta. So we'll see. Yeah. So yeah, I think that's all we have time for. Yeah. David, do you have any closing thoughts? Or Johnny?
All right. I guess thank you guys for listening.
Yeah.